Hello everyone and welcome back. So in this video, Lee is going to be implementing the 2D GetValue functionality.
Right. What we're trying to do is actually over there, this video and the next two videos, is we're going to whittle down and get rid of all of this functionality that is inside of the game manager. Well, except for this timer part. But we're going to pretty much try to or we're not going to try, we will encapsulate all this into the methods that are part of the noise library itself. So let's jump over to noise and go ahead and collapse these. Let's implement our first GetValue method. Now this is going to be a public. We're not going to make it static. It's going to return a color, and we'll call it GetValue. Now, GetValue is kind of chosen because once you start messing around with textures inside of Unity, they use getPixel and getPixels. And if you've ever messed with libnoise, they use getValue as well. So I'm just trying to keep things kind of consistent. You know, trying to replace my complete and utter lack of creativity with names.
Oh, come on.
But now we need a couple of arguments. So this will be our x in and our y in. Oh yeah, probably should tell it what type y in is going to be. That might make it happy. All right, now we need to return a color, but we need to have a variable to hold to create our color. So we're going to make a variable called noise. We're going to initialize it to 0f, and then we're going to return a new color that will be created by setting noise to be the R, G, and B values. We're going to set alpha to 1. So, and then there goes my alarm. Someday I'm going to have to find that watch. So, all right, so that is our initial value. We're going to need a couple more variables in the beginning of this. One of these is going to be our signal. This is also going to be set to 0f. This is the value that's going to hold the value that comes out of noise or out of our noise algorithm before we do some manipulation to it and add it to noise. So signal is going to be a part of the inner loop of our octaves. So each time we're in an octave and we're looking for noise, that initial call to our noise method is going to be saved in signal. We're going to process it, and then we're going to save the cumulative result inside of noise. Once we're done processing all of our octaves, the value in noise is what's going to be used to create our output color.
Okay.
We need to keep a value to hold our persistence. Now this is our local persistence as opposed to our instanced persistence, from our property up here. Persistence is going to start off at a value of 1, and every time through it, we're going to multiply persistence by the property of our noise. So if our persistence is set at 0.5, our first octave's noise is going to be, or our first octave's persistence will be 1. The second one will be 0.5. Third one will be 0.25, followed by 0.125. I think it's 0.0625 after that, and on and on and on, and continuously updating per octave. And if our persistence for our noise is set at a greater number, let's say it was set to 2, the first octave would be at a persistence of 1, second would be 2, then 4, then 8, etc., etc., etc. But we need to keep this local so we can increment it through each octave. Now, these next values, I'm going to be modifying the x in value and adjusting it for an offset. Now this, I don't know how to explain it other than it's kind of a workaround. If in the earlier videos, we were discussing an artifact that was showing up, an optical illusion that was happening to our noise as we were offsetting our octaves, and as our noise was convolving towards zero, we were getting artifacting lines that were showing up, and that was an illusion based off of the way our noise was being sampled. To fix that, we were shifting our noise off to a side and relying on that. Now, the problem that we have with just relying on the way that we were doing it before, which was taking twice the size of our texture and adding it to our X value, is with this library, there's the potential of somebody taking and putting in a negative X or a negative Y, and then the noise, or if we were to just use that method, and let's say we had a texture that was 512 by 512, and they put in a starting position of negative 256 by negative 256, that would mean our 0 in X and Y would be right in the middle of our image, so we're going to run across that problem. So to eliminate that possibility, well, not completely, but reduce the chance of that happening, is I'm going to add a million to both X and Y, because the likelihood of somebody adding a million or a texture that's a million pixels across is not going to really happen. I think it would explode the computer before that would ever run through correctly. I also want to take our offsetted X and multiply it by our frequency. So our frequency is basically, in effect, going to be a scalar. Now, the other reason I chose a million is the fact that our world size tentatively right now is no more than 40,000 meters in any direction from the world origin. So that's taking that into consideration, saying that if I do a million and I were to literally sample at every meter point along our terrain, I wouldn't cross zero. So it's just a magic number. I like magic numbers. And then we're going to do the same thing for our Y in. We'll add a million to it and multiply it by frequency, which acts as our scalar. Now we have to deal with our octaves. So we'll do this by having a for loop. We'll call it I. It's going to go from 0 to be less than our number of octaves, which we hold in octaves. And then for each of our octaves, we need to sample our noise. But the way we've got things set up right now, I want to use GetValue to be able to sample regardless of the type of noise. So if somebody defines the noise as simplex or as value or Perlin, I want that noise to be sampled without having to have a different method for each and every type of noise. To do that, I'm going to wrap up our sampling based off of our noise type. So I'm just going to make some conditions, some ifs and else ifs, that says if noise type equals our types dot value, then we're going to check for our value noise. So we're going to set signal to be equal to our value of X in and Y in. I'm going to add 1 to it, and I'm going to divide it by 2f. This is performing the operation because our noises spit out noise in the -1 to 1 range. This is going to offset it so that our signal is going to be in the 0 to 1 domain. The reason why is our GetValue is going to be passing out a color as opposed to a float. So we can't use negative numbers inside of the construction of a color, just the 0 to 1. And I'm going to take those 2 lines of code. I'm going to duplicate them 2 more times. And I'm going to set this one to else if. And this last one to else if as well. I'm going to check if value type noise is equal to Perlin. Then we're going to run the Perlin noise. And if we're equal to simplex, we're going to run the simplex noise. So this will give us a signal being whatever type of noise is currently set for this instance of noise. Once we get our signal back out, we need to add it to our noise, which we're continually accumulating our noise for each of octave. So our noise is going to have the value of signal times our persistence added to it. Now this is our local persistence, not our, let me define it, it's actual in scope the GetValue's local persistence, not our persistence property, because we're going to be modifying this persistence for each octave. So once we've added that signal multiplied by our persistence to our overall noise, we need to modify the X in and the Y in and persistence for the next operation, or the next run through the octave loop. So we're going to divide it by our lacunarity. Do the same thing for Y in. This is controlling how much spacing is going to be between each of the different octaves of noise. Once we get this all done and we've got our little interface that allows us to change the numbers on the fly, it'll be easier to see what exactly that does. And we're going to take our persistence and we're going to multiply it by our persistence property. Once we've gone through all of the octaves, we're going to do a little bit of processing on the last noise. So we're going to take our noise, we're going to divide it by our octaves. This is going to average it out, but because we've got persistence running, not all of our octaves are going to be the actual weight. So the problem that we run in is if we're just to average our noise, you'll find that if persistence is anything between 0 and 1, there's the potential to take our noise and drive it too far to black. Or if our persistence is greater than 1, it will blow out our noise. So we're going to take the result of the noise divided by octaves, we're going to multiply it by our gain. This will allow us to be able to correct the exposure of our noise. Once all of that's been processed, our noise is going to be added to the red, green, and blue channels of the color that gets returned out for GetValue.
Nice.
So if I build that, we get no errors. We can go back into GameManager. Now, we've got our noise. We're defaulting our noise. I can go through and I'm going to leave it for now, though I could erase it. I'm going to take our overall loop. Forget it. We don't need it. I'm going to take all of this. This is our octave loop with our samples each through and our count. We don't need any of this anymore. We also don't need the count. Our value for n, we're not going to need either because we're returning a color out. So we can get rid of that. We're not going to need to modify X and O anymore. That's all handled internally. So now we've taken all of that, boiled it down to a single line for setting our data, and that will be noise.getValue. and into that we send X and Y. I should be able to simplify this even more by deleting the brackets. Hitting F6, build. Now, if everything works fine, we should get a non-moving texture.
Hey!
And look at that. And our time is at about 32 milliseconds, which we expect for simplex noise.
Very cool.
Now, if I wanted to change our noise, let's say I wanted to get purlin noise. There we go. If I wanted purlin noise, I'm going to choose purlin noise because at static, simplex, and value are fairly close. But if I wanted to switch up to purlin noise, all I have to do is go noise type equals noise types dot purlin. So if we run this,
Very
we
nice.
get our purlin noise.
Mm-hmm.
And our time is different as well. All right, so that implements the get value in 2D. So in the next video, we're going to come back and we're going to implement get value for 3D noises.
Fantastic. All right. Well, with that, that is going to wrap up this video. Thanks a lot, everyone.